The significance of concavity. For each of the following situations, sketch a reasonable graph of the relationship between the quantities given. Write down the intervals on which your graph is increasing, decreasing, concave up, and concave down. See if you can relate the concavity to the description of the situation. 1. A model rocket is launched, then falls back to the ground. Graph the height of the rocket, plotted as a function of time. Okay, so height as a function of time, that means that height is here on the vertical axis and time is on the horizontal. So presumably the rocket is starting from ground level at time t equals 0, that's here. And then the rocket is going to go up and it's going to slow down, slow down, slow down until it reaches some maximum height. And then I don't know whether or not there's a parachute involved, but let's assume there isn't, in which case it's going to come hurtling back down to Earth and eventually hit the ground right around there. Okay, so then the graph is increasing on this interval right here, and the graph is decreasing on this interval, and then the graph is concave down the whole time. I say that because the graph is bending downwards the whole time. Okay, number 2. When a new product is advertised, people are slow to adopt it at first, but as word of mouth spreads, more and more people try it. However, the rate at which new people try it slows as time goes on. Graph the total number of people who have tried such a product, plotted as a function of time. Okay, over here, we've got number of people who've tried the product, and then t is time. So the idea here is that people are going to be slow to adopt it at first, but there will be more and more people who have adopted it no matter what. You can't try it and then go back to not having tried it. So in this case, we're going to have a function that's increasing the whole time. So at time t equals 0, let's suppose that nobody's tried it. And then we're going to be slow at first. So we're going to be increasing but slowly. And then it's going to speed up as more and more people try it. So more and more people try it. So the number of people is going to increase kind of rapidly. But then as time passes, we're still going to have more and more people try it, but the rate at which people try it is going to slow. So it's still going to be increasing, but maybe slower and slower. I suppose it's got to level off at some point. You know, there's only a certain population in the world, and if we put that population up there, we'll never exceed that. So presumably there's some horizontal asymptote. Now, probably not everybody in the world is going to try this product, but we could certainly never get above that world population. Okay, so what can we say about increasing, decreasing? Well, this function is increasing the whole time. As we said, once you've tried it, you can't go back to not trying it, so it will never decrease in terms of the number of people who have tried it. And then the concavity actually changes. So in the beginning, this function is bending which way in here? Is that bending up or down? That's bending up. So we're concave up until we get to a certain point. And then once we get to that certain point, we begin to change. We begin to bend downwards. And so I think that the winning point, the place where the concavity changes, is roughly here, the way that I've drawn it. So in this beginning part, we are concave up. And then for the rest of the time, we are concave down. Number 3. A car starts slowly and then speeds up. Eventually the car slows down and stops. Graph the distance that the car has traveled, plotted as a function of time. So over here we have distance, down here we have time. The car starts slowly and then speeds up, eventually slows down and stops. So the total distance traveled. So the distance traveled is going to be, well, I guess we won't have traveled any distance originally, but then we're going to travel some distance, slowly increasing our distance traveled. But then it says we speed up. So as we speed up, the distance that we cover gets grows faster and faster. But eventually the car slows down. So we're still moving forward. So the distance is still increasing, but it's going to slow down. We're not going to cover distances rapidly. And then the car eventually stops. So when the car stops, let's say that the car stops right there, what's true about the total distance traveled, even as time passes? I don't want to stop the graph there. This graph continues. So really think about what's happening to this graph as time passes. Well, the distance isn't changing. It's exactly what it is at that moment. So at some point, it's going to become horizontal. So in terms of increasing, decreasing, I guess I would say it's increasing until we get to the stop. So increasing until, say, that moment right there. And then once you get past the stop, I wouldn't say that it's increasing, and I also wouldn't say it's decreasing. It's just constant after that. So maybe we can write that. Constant. Function is constant from that point on. Okay, in terms of concavity, I think we're going to see something similar to the graph that's right up above. So in the beginning part here, we are bending upwards until we get to some critical spot when the graph changes, maybe a little bit further, just an estimate, until the graph changes and begins to bend downwards. So just like up above, I think we are concave up and then, concave up until a certain point and then concave down. So it feels to me like the point is right around here. That's an estimate. And inside of this interval, we are concave up. Remember, it's only the x's that we're thinking about. Inside of here, we are concave down. And then the rest of the time, I'll put it here in blue, there's no concavity. It's not concave up or down, it's a line. Moving on to the next page. Number 4. A cup of hot coffee is standing in an air-conditioned room. Graph the temperature of the coffee plotted as a function of time. Temperature over here, time down below, temperature of the coffee. So presumably the coffee is pretty hot in the beginning, so we'll give it some high temperature right there. That's the initial temperature. But it's sitting in an air-conditioned room, which means the coffee is going to cool off. So the temperature's got to be decreasing, but there are a few different ways the temperature can decrease. It can decrease at a constant rate, it can decrease like that, or it can decrease like that. Only one of them makes sense in the scheme of this problem. Hopefully we see that the coffee's temperature is going to decrease pretty rapidly in the beginning, but then it's going to decrease less and less. And will it eventually get to that horizontal axis? Well, only if this room is really cold. I'm going to put in another line here, another horizontal line. I'm going to put right over here room temperature. I'm going to try to put over here room temperature. I'm going to draw this dotted line here. And that's the lower bound. We're never going to get past room temperature. We will get very close to, probably close enough that we'll say, oh, it's reached room temperature. But this is what the graph looks like. So what about increasing, decreasing? It's decreasing the whole time. Technically, I don't think it ever gets horizontal. It always decreases. Even in this last little piece, it's still decreasing just a little bit more. And what about the concavity? Well, as we run along this curve, we are bending which way? We are bending upwards. So this graph is concave up the whole time. Number 5. A skydiver jumps from an airplane, falls freely for some time, and then pulls the cord to open her parachute. Graph the height above ground of the skydiver plotted as a function of time. Okay, let's draw our graph. Time here, height of the skydiver here. Okay, so the skydiver jumps out of a plane, has some height that's pretty high at that moment, and then begins to fall. And as the skydiver goes into free fall, what's going to happen to her height? Well, clearly it's going to decrease because we're going to be falling down towards the ground. Is it going to decrease slow then fast, fast then slow, or at some constant rate? Again, only one of these makes sense in the problem. Hopefully we see that the height is going to decrease slow and then faster, faster, faster. There is such a thing as terminal velocity. So if you understand stuff about terminal velocity, then you're going to draw a more accurate picture than we're going to write here. I'm not going to assume anything about terminal velocity at this point. Let's just assume, I guess, that she's going to pull her parachute before she reaches terminal velocity. And so she's decreasing faster, faster, faster. But then we get to the place where she pulls her parachute. And once she pulls the parachute, well, she's still going to be coming down to Earth, but presumably at a much more leisurely clip. And maybe we could say something like a straight line, something like that, and eventually hitting the ground. So I don't know that that's exactly true. I've never parachuted myself, but I assume that when you are falling with your parachute open, your velocity is pretty constant. And so your change in height is going to be pretty close to a straight line. So let's talk about increasing, decreasing. So this function is decreasing the whole time. Something funny happens with the concavity at the moment we pull the chute. So we're going to put a dot right there and ask what's the concavity to the left of that space. So this curve is bending downwards. So that means that in here, the curve is concave down. And then what about the rest of the time? What about all of this? Well, it's a straight line. Is it bending up or down? Neither. So I would say there's no concavity.